talk is focused on one aspect of my work, which is about healthcare delivery, and in particular, the idea of getting ambulances to people. In general, my work focuses on complex systems design with connected physical infrastructure. It could be anywhere from logistics systems, airline systems and airport systems, and emergency medical services and other healthcare delivery services. And I bring a host of tools to these, ranging from data mining, prediction, optimization, simulation, with the goal of planning for these systems. How do we design them before they're put into operation? And how do we look forward as we design these systems? And as we get near real-time information, how do we reconfigure them so that they can serve the needs of the various stakeholders of the system, considering the different kinds of potentially conflicting stakeholders' ideas and their different needs. We also focus on, as these systems are being put into operation, and often the world is uncertain, and as these uncertainty manifests, how do we repair and recover these systems so that they perform and function robustly to serve the needs of everybody involved? So I'll focus today on the emergency service aspect of my work, and I'll bring particularly the focus about emerging settings, including those in India. This is one snapshot of a city in India, and you can see that near the center of the city, you have this quite dense cluster. What you have as in the picture are calls, which we have a balloon here, and we have a wheelchair symbol in it. And wherever we have another balloon with a plus symbol in it was where the ambulances were located across the day during the functioning of this particular emergency service in a city. This was a while ago, but this serves to indicate how much the demand is increasing for these kind of services across different cities in India. About 10 years ago, only about 10 states, and that too major cities in each of these states, were having these centralized emergency service systems. More and more, like most of the people in the audience would already know, systems like 108 are coming in many, many more cities. And what we want to look at is, how are these systems designed? What is behind the engineering of these different systems when we want to serve the population? How do you think about it in the context of the entire city, the entire service region of interest? So here again, just to emphasize, you have the plus sign indicating the bases. That is where the ambulances are located. And these bases were in some sense prefixed by the operator. And then we have all the calls arriving. And of course, we don't know where the calls are going to arrive. This is a stochastic process. And basically, there's a lot of uncertainty in where calls might arrive. So you have this entire system. For now, ignore the white and red and greens for the colors. I will tell you later what they mean. So this problem is when we play this out over time, calls keep appearing at various places, and you have ambulances that may be busy or free at the time. And so you have to make decisions. As the operator of the system, multiple decisions have to be made. So let me focus on what happens to this notion of ambulance provision, or formally what is known as emergency medical services, in the context of emerging economies. So first of all, these systems are highly resource constrained in these emerging settings, because as the fleet size and other provisions are being made, you can have very few ambulances per capita. And prior to these 108 type centralized providers that are being put into place, previously there were no centralized providers. So what used to happen was there were these ad hoc taxis or hospital ambulances that were used to provide these services. So you call maybe a particular hospital and say, can you send me your ambulance? Or somebody would just take a taxi to get to the hospital. And part of this was due to the lack of awareness of what is called en route stabilization of the patient. So the idea was simply, can we get to the hospital rather than as we get there, and before you even start to think about where the provision of health begins, that is, as soon as somebody reaches the patient, tries to do some stabilization on scene, where the patient is first, and then take them to the hospital, and en route as well, do any kind of other stabilization needs that are required before the patient can be admitted to a hospital. So some lack of awareness was present in the system, and therefore there was this not a differentiation between an ambulance and maybe a taxi, which is simply a means of transportation. And when we think about systems like India, Africa, and many other cities, we're thinking about very large scale cities. What I mean by that is very densely populated areas. And also these are served primarily as a public-private partnership. Primarily these are state funded, and therefore the state's objectives in serving the entire population take precedence over a private partner's or the operator's preferences here. And so the operator is working on they design and operate the system, but they are responsible and accountable to the state in what kind of metrics are actually they optimize for and how they serve the system. And it takes a lot of time, almost the first 5 to 10 years for users. That means the average person to adapt to the system and understand what's happening. And so you have this interesting framework of this 108 centralized system that's layering on top of these existing hospital ambulances or taxis or other existing frameworks in the system. And I'll focus on these different aspects of these. In fact, I'll bring about what are the unique aspects that are different from, let's say, other mature emergency medical service systems across the world. And I'll bring about different, this sequence. I'll talk about the data a little bit, how data was used, what kind of mathematical models were used, and what kind of decisions we aim to make using those mathematical models, and finally, what the impact was of such mathematical models. So we have these goals, which are strategic as well as tactical. And the strategic goals are that of saying, what is the size of fleet that I need to have? And what are the locations of the ambulance bases that I need to have? Some of these are dictated from practical considerations, others using the mathematical considerations. From a tactical point of view, I have some other objectives. Where do I locate that fleet? Let's say I have base locations and I have a fleet, but how many ambulances in each base? And during the day, do I need to move the ambulance around so that if there are peaks and valleys occurring, how can I actually address such peaks and valleys as they occur? And next, another question of what to dispatch. That means if a call arrives at a particular location, then which is the ambulance? Where is that located and who needs to go serve that particular patient? So for example, this is the problem of saying, take that fleet and locate it across the entire city. And once you have that, demand keeps occurring across the city, of course, in an unpredictable stochastic manner. And how do you actually use that information to actually locate these ambulances? And then as that demand may change during the day, maybe I have to relocate or redeploy some of those ambulances through the day to really answer the needs of the population. Despite the resource challenges, what are the big advantages in these particular cases? One is that you have a tremendous data collection system that is set up in place because of the IT infrastructure and all the cell phone traces, GPS traces, and other things that these ambulances are equipped with. We actually have information about different things, how movements were happening based on historical data, where demand was occurring and how did that change, whether seasonally, on a daily basis, or on a weekly basis, and so on. And so we want to estimate different things from that particular data. We want to estimate things like arrival rates and call patterns and travel times and so on. And we want to use that to be able to serve this system better. Okay, sorry, 1 second. I guess I have to share the screen again here. Okay. Okay, so let me talk about some challenges which are unique to these emerging settings. There are these high resource constraints and a lot of traffic congestion in the system. That means as the ambulances are moving, they may encounter, because of limited road infrastructure, they may encounter slow movement times, either due to traffic or due to the road conditions. Then these influence significantly what response looks like. And response is one of the most important things that we care about in terms of how quickly can an ambulance get from where it's located to the patient. That means that from the patient's point of view, what we care about is when did they call and when did they actually have an ambulance arrive to where they are. So that's one of the novelties of the system. The second is a notion of human behavior, which I will explain shortly. The other is this idea of the decentralization of ambulance services. And then I'll talk a little bit about looking to the future, how medical drones, both in emerging settings and in mature settings, are being used to actually serve people and improve service levels across cities and across regions, which may be served at very different levels. So let's look at the first novelty aspect. And in this case, given these different challenges of high congestion and low resource constraints, the question is, how do you best locate ambulances, right? The first is we use a multi-level approach. At the first approach, we are learning from the data, what the demand rates look like in different regions of the city, how to actually even separate the city into regions, and then estimate from historical data and evolving data what demand looks like over different periods of time. Is it a similar pattern even though there's stochasticity, or does that pattern change and have peaks and valleys across the day or across days of the week and so on? We also learn traffic patterns. That means between the same 2 points, when we want to send an ambulance, which is the fastest ambulance might change over a day. That means if there is a bridge between base one and let's say a particular neighborhood, and there is just the regular streets between base two and a neighborhood, in the morning times, it might be easier to cross the bridge and get from base one and serve people in that neighborhood. But as traffic increases, it may be possible that during the day, crossing the bridge becomes much harder. Therefore, the nearest ambulance is actually from base two or a different base, but not from base one. And we want to capture those evolving characteristics. So we use data mining and learning for that purpose. We also want our system to adapt to different modes of transport. In different cases, for example, in places like Assam, there are water ambulances. So we want to capture how speeds vary when you have the road ambulances versus, let's say, the water ambulances. And that can be captured in the kind of models that we have. And then we want public acceptance. Maybe ambulances are slow because people do not realize that they have to give way to ambulances in a more instinctive fashion. And that, because the system is still adapting, that takes time. So we capture all of these in what we call as system or city characteristics. And then we plug these all into a model which makes decisions. And that is based on a combination of simulation and optimization. And the statistical, we want the simulation model to be statistically significant. And that could be based on simply a kind of model that I'll show, or a queuing model, or many different sophisticated mathematical aspects that could fit in there. And then the optimization algorithm is a decision-making framework that says, I embed the simulator into the optimizer and understand something about the objective to get near optimal decisions. And in this case, we are making those decisions about where to locate ambulances and where to redeploy them as the day progresses, as we see what is happening through the day. And if we forecast what's happening, how can I move ambulances around so that they best serve the demand of the city? And here I want to give a shout out to my co-authors on these different papers, and those who are interested in looking at some of the math can reference these papers that are here, and they're available on my web page as well. Okay, so let me tell you why this problem is hard. Why do we care and why it is hard, right? If it were very easy and if I could just locate things across the city, it should be fairly straightforward, right? So let's think about this system. Let's say I located 4 ambulances across the city using this in this simple example, and they're located here before, let's say, the demand starts evolving through the day. Let's say I get my first customer, I send the nearest ambulance to that customer. And then another customer comes, they could have been served better if this first ambulance had been available. But then I send the nearest one available at that time, which would be that. And so there, let's say served in 30 minutes. And another one arrives. And that could be, that demand point could be here. And that I send the nearest ambulance. And when this particular demand arrives, it could be that the nearest ambulance at that time could be much farther away, and maybe that caller has to be turned away. What happens is, because of what happened in the past and how demand evolved over time, we get what is called dependencies in these systems. So all these decisions about where to locate one ambulance here and one ambulance there and other things are interlinked. And why are they interlinked? If I had a lot of resources, if I had many ambulances, we would not have these interlinkings. But the fewer resources I have, the tighter systems are coupled. And therefore, we have dependencies arising in the system as demand evolves. And of course, demand is unpredictable. So if I knew it, of course, I would have placed things better. So if I knew more about the system or about demand patterns in the system, perhaps I would have done this. That means move that ambulance from there to this point. And that means I could maybe have served these callers in this pattern. Of course, this is if I knew what was happening, right? If I knew how demand was going to evolve. But what I can do is, with my predictions of demand, understand not only one sequence of how demand evolves, but sample many tens of thousands or millions of such sequences of how demand might evolve, so that my decisions can be statistically significant. So if I change the allocation of ambulances in the system, the dependencies change. In fact, the dependencies are fewer in this system. So if I can have a way to arrange my resources in the system such that the dependencies are fewer, then I have better service levels for all the population. That's the key idea. Can I represent what's happening in the system, maybe as a graph using a simulation framework, have costs on the allocations, which would be the arcs represented by these graphs. And as I break more and more dependencies, I add ambulances or reallocate ambulances across the system, I have fewer dependencies, which means better and better service levels. Okay. So what we do is embed this within a greedy simulation optimization algorithm by actually considering the nature of the objective function that is described by these graphs. We exploit a property called approximate submodularity. And I will not get into the proof of that, but the idea is, can you understand the technique of what is happening precisely and the underlying mathematics so that I can make a better decision? Suppose I want to allocate n ambulances among m bases. This greedy algorithm adopts a strategy and says, suppose I have 0 ambulances in the system currently, test adding this ambulance at each location and simulate this over millions of different paths of calls. That means these are different probability paths. These are coming from the data mining and analysis that we did previously. And we said these are the patterns that are evolving. So those patterns are embedded within the simulator, and we say, where is the best way I can allocate the first ambulance? And locate that ambulance there, fix that there, and repeat. And this is a specific algorithm called a greedy algorithm. And it turns out under certain structures, this can do very, very well. And so essentially, what we are doing is leveraging that mathematical property to do what's called a very highly tractable, that means a system solution algorithm that runs very fast, but also gives us very good decisions. We also show in the papers that these decisions are close to optimal in the setting that we are looking at. And we can solve them very fast, which means I can use it for when I plan in the beginning of the day where to locate things, or during the day as ambulances become free. Some ambulances which are idle can be repositioned across the network, and I can do better service by moving them across the network. So what we find is based on different objective functions. We care about how many people are served within these thresholds of 15 minutes, 30 minutes, and 60 minutes, and so on. We find improvements in all these metrics. And fundamentally, what is the one metric that's the most impacted? The number of cases in which earlier people were told that the ambulances are busy and we cannot serve you. And that dropped from what it was to 40% of its original number. Right? So we were able to show that many more people were served. People who were earlier rejected service were now allowed to serve. And beyond that, we can show that instead of simply locating ambulances in a plan and then leaving them as they are, after they serve, they come back to the original location. If I'm able to move them across the network, predicting what happens in the next half an hour, 1 hour, or these different intervals of interest, we can do even better. And again, the most impacted metric is how many people you can reach using these, the number of callers you can serve as you are able to redeploy and place ambulances in a better way. We also, of course, find improvement in the number of people served within the thresholds of 50 minutes, 30 minutes, and so on. But this is the one that's the most impacted. That means people who would have been turned away are now being able to be served. So that was the first story. That means better math, understanding the underlying math, can help you do even better with respect to these different services. Next, I want to talk about human behavior. As these systems were being adopted, people were responding in interesting ways because they were seeing a system where previously they were either taking taxis or sometimes calling hospital ambulances, and now these other systems were also in play. So how do humans react to this? And interestingly, in the emerging settings is where human behavior is of the most importance. And these influence the first 5 to 10 years of operation of the system. So we really care about how humans are understanding and adopting these systems. So there is a phenomenon that happens that customers, because they now realize they have access to multiple providers, and because they're in an emergency setting, they're of course panicking, perhaps not knowing what to do. They don't have the required medical knowledge. They call the different providers that they want to, or as many as they want. So for example, this patient can call 2 different providers and choose the one which arrives first. It could also call a taxi and depart by that. And so ambulances, we observed, were, even though they were actually trying to serve a call, so we were finding that ambulances were going to serve a call, and then they were finding that the patient was not present at the scene. And of course, the ambulance did not know when the patient lost their willingness to wait and left. They were not willing to wait anymore, either because a taxi arrived, they had a private vehicle, or because the private ambulance arrived, or something else happened, right? And so we wanted to understand what was the patience of the different customers who are using the system. What is the willingness to wait? And can we match that willingness to wait better? So it's not, service is now more nuanced in the emerging settings compared to other settings. It's not just simply sending an ambulance and getting there, but the customer actually being there and us serving them. So we add to this the data inference model. Here we look at past data, and even though we do not actually know when people left, we are able to estimate based on different characteristics of populations. And primarily, it turns out in this case, whether it's an urban or rural area and the kind of emergency that people are calling for, which they would have told the dispatcher on the call, those things influence how long they're willing to wait. And these, using statistical models, we are actually able to estimate these. This is all hidden information, which is called censored information. But if we have good statistical and historical data, we can significantly and accurately estimate how long people are willing to wait. And we estimate the true patience of these different callers. And these models are updated as data is updated in the system. And this can again be embedded within our statistical simulation or queuing based models to optimize for where to locate ambulance. Now we said, well, the current locations of ambulances, the current bases themselves might have locations so that they're not able to serve people well enough. So we said, oh, maybe there are even more important considerations that we need to think about. These are, instead of simply looking at shorter term things like where to locate ambulances, which bases to put how many ambulances at, we said, do we need a larger fleet size to serve this population because many people are leaving the system? Or do we actually need to move the bases around so that they better match people's willingness to wait for the system? And so we undertook that study. The first result was we understood how different sections of the population were able to wait for ambulances. This is called a statistical model for these data, which is called the interval censored data. And using these maximum likelihood estimation models, which are based on a proportional hazards rate, which means that over time, we estimate that people are less and less likely and willing to wait. But what is the rate at which they might drop out? And what kind of populations are affected? And so we can classify these people into urban and semi-urban or rural, and the kind of emergency they're calling for, whether it's a type 1 or a type 2, or more higher priority or a lower priority. And we also simultaneously say, suppose every street corner of the city were considered a potential base location for ambulances, which is one of the largest models solved in the literature with 13,000 potential base locations. And again, we use that greedy algorithm that I talked to you about. Can we match people's patients to the way the system is, how we locate ambulances and therefore serve more people? And then we found that compared to the existing base locations, which were in blue here, our system was suggesting, suppose we had the same number of ambulances, where to locate bases. Suppose we could increase the fleet size, where to locate the bases. If we could, this was a double the fleet size. This is what triple the fleet size. If you triple the fleet size, we can match that of what is there in more mature emergency services. But of course, we do not have that ability. Now, what we also show is instead of just tripling the fleet size and not changing the base locations or doing network design, if we do both of these in conjunction, we can do successful service far better. So this green curve is where we actually redesign both the bases and look at various fleet sizes. So with the current fleet size, I can serve, instead of less than 80% of the population, I can serve about 84% of the population. But as I can increase the fleet size to different numbers, now I can say, both redesigning the system from a more fundamental level of where to locate, using these street corners as potential locations, but also potentially increasing fleet size over time, can further and further improve service levels in the system by matching how people behave to how the system can serve those people, capturing their behavior correctly. That's the second story. The third story, which I'll speak in, the third and the fourth stories, which I'll speak in much shorter time, so we can have time for questions, is about this notion of decentralized services. So here, This is a unique setting for these emerging economies, including India. And here we use the notion of game theory to model how these service providers themselves are reacting to the fact that people are calling multiple providers. And I'll skip over the mathematics here. But we find that if we think about, if we compare competitive behavior versus centralized behavior, we find that there is an interesting phenomenon. If customers call multiple services, that of course the providers or the different emergency services are going to realize, oh, customers are being strategic here. They also take their own strategic decisions of who we provide service to, what is our coverage or catchment region. And based on that, in fact, that decision, again in reverse, influences the customers. In fact, customers are the ones worst hurt by the strategic behavior. So their strategic behavior, which is myopic, influences how providers behave, and in turn further affects and spoils, deteriorates further the service level that customers achieve. It also reduces equity in society. We can also talk about what kind of bargaining mechanisms or centralization mechanisms government can incentivize, and what are the costs of doing so, what are the incentives government can provide, so that either these different services can bargain with each other, provide better service levels to society, or can you centralize the system, and what would be the impact of that. So I'll just skip over the details of that, and I'm happy to answer any questions. Here is a futuristic idea that is, well, not so futuristic. This is being tried in countries like Canada and Sweden. The idea, and it's also being tried a little bit in India. There are apps which allow people who are CPR trained and others to come and quickly perform CPR to, let's say, a particular person whose family may not know how to immediately address that. So if there are trained personnel across a city, whether nurses or others, or even other people with other kinds of um, uh, uh, or even people with other kinds of emergencies, if people know how to address them, you can have a bystander, somebody who's nearby, come and address this. So an addition to that is to have a drone, a medical drone, fly through the air from its base. Maybe it's closer located than the ambulances, and they're spread out across the city. And these medical drones can come and give you a defibrillator, which can be applied to the patient. And it's very safe. It does not actually affect patients who are healthy, only those whose heart has fibrillated or stopped. So this affects the highest percentage or the most acute of emergencies, which requires the highest or quickest service levels. So there are apps such as Emergency and Jeevan in India, Pulse Point in Canada, and so on, that actually try to serve these with or without the drones. And so we were trying to capture, if we looked at a stylized model of a synthetic city, if I want to serve all these high priority emergencies within a threshold of 8 minutes, let's say 90% of the time, then what can we do? If we did not have drones, in this case, we could say that the maximum service level we could achieve was 75%. If I just increase the ambulance fleet size, we could achieve 85%. It turned out that still some regions, based on how the basis was structured, could remain uncovered. But when you think about the medical drones, they can be spread out more over the city than ambulance bases, which require the infrastructure to be set up for them. So if you could spread out medical drones more over a city, we can find that, for example, these yellow points are where drones could be located and how many are located at each point. We see that the overlay of the yellow heat map on the red heat map shows how much better you can serve. But of course, we're also capturing how people respond. So if we have these bystanders responding at different speeds in urban or semi-urban or rural areas, how can we improve service levels? Does having medical drones help at all if people are not involved? And so on. So we can answer these questions which are related to the upcoming frontier of emergency services and what we can do to actually address and answer these upcoming questions. So again, math is involved in understanding the data, trying to solve for the kind of how to model and capture that data correctly, how to solve for the right decisions we want to make, and what is those impact, or what kinds of decisions, what kind of solutions will have the most impact, where should a public provider put their money, how can I serve more people well with the least expense, and so on. So I'll stop there and take any questions.
Thank you so much, Professor, for that fascinating peek into how we can actually allocate resources using mathematical models. It's a rather new field for what I suspect most of our audience is. And thank you so much for telling us more about it. We've had quite a lot of questions coming in.
Mhm.
The primary one being, what are the main challenges in applying such a math module in a country that's as densely populated and dynamic as India?
That's a wonderful question. And that is where data helped us. And this is, I want to draw attention to how the understanding of the underlying system, the fact that the systems that we were working with, the operators that we were working with actually collected data historically across the system, helped us tremendously. We could not have been running blind, so to speak, if we did not know the kind of patterns that were evolving. And I also want to emphasize that we use historical data, but it's also important that as data is being collected by the system in real time, it's important to incorporate that data and learn from it as we go ahead. Like the aspect of human behavior that I mentioned, for example, that's been evolving over time. The same city, if we look at 10 years before versus when we look at now, humans change. They understand more about the system and therefore they adapt. And in turn, the operator and others also have to continuously adapt. And that's where, again, using the math and using it in the right way becomes very important. So learning from it is extremely crucial.
I see. Thank you so much. I believe we don't have time for more questions, but thank you so much for a fascinating talk. And our audience members can find links to your work in the chat. And I invite them to please absolutely check out more of Professor Lavanya's work if they're so inclined.
Thank you, Misha and Shruti, for having me. Thank you, India Science Festival. It was very exciting being here, and anybody can contact me if they have questions.